Hello. So this is problem 4115, 415, I mean. Okay, so the cantilever shown in the figure consists of two structural steel beam channels, size 3-inch, 5-pound force per foot. Using superposition, find the deflection at A, include the weight of the channel. Okay, great. So first, let's start with the Castigliano's theorem. It says that the deflection equals the strain energy. I think strain energy over or with the partial derivative of the strain energy in terms of F with respect to F in the same direction. So the F same direction as the deflection. So in beam bending, we derive this in the lectures. We, pretty much just the professor. I was taking notes along with it though. But so U equals, for beam bending, U equals the integral of from 0 to L m squared over 2ei with respect to x. So once we put use the Castigliano's theorem, we put this is U, right? So we put this in the partial derivative. So here, and then okay, from here we can take out the constant and the integral. And then we can use a partial derivative of m. I mean, m doesn't look like, what is it, f? The partial derivative of f. But f just means like the force. So like here, moment, it would be the force. So once we find the partial derivative, we have to use a chain rule. So we have it here. So we take this squared out and put the 2 in front. So 2m. And then times the partial derivative of the inside, which is partial derivative of m with respect to f, which we don't know yet. So right here, the 2 cancels out, and then we get m over ei times the partial derivative of m with respect to f, and all that for the integral from interval 0 to L with respect to L, and then all that equals bring it back, is the deflection of A. So let me move down real quick. So m in the equation is the initial bending moment. F is a point load at the free end, 150 pound force. And then E is the Young's modulus, I is the moment of inertia. So it told us that it was steel. Steel is 30 times 10 to the 6 psi. I is, it says in the Shigley textbook that it's 1.85 inch to the 4th. And then since there's 2 of them, there's the moment of inertia is 3 times 0.70. And then the distributed load. So let's see, it says the weight of the channel was 5-pound force per foot. And since there's 2 of them, there's 10. And then once we convert the units, so take out feet and put in inches, we get 5/6 pounds per inch. And then also there's a load in the diagram above. It didn't say in the problem, but it said it showed in the picture. So that is 5-pound force inch. So when we add them together, it's 5.833 pound force over inch. And then point load, I said point load, which is given in the problem or in the picture, F equals 150 pound force. And then the length is 60. And then, yeah, so now we can use the principle of superposition to find the moment. So we make the cuts. So we do this by making the cuts, and we can do the point load first. So if we kind of look at this diagram, so there's the point load, and if we make a cut at point X, and we calculate the moment, the force is X away, so it's negative, or yeah, and then the equation for the moment is force times length, right? So force times length is F times X, and then there's a negative because of the convention, sign convention, the frowning face, it bends the beam downwards, right? So that's why there's negative. And then there's also the distributed loads. So in summary, A equals this. Gotta make sure it doesn't turn off. Yeah, okay, cool. So in summary, it equals this, but to kind of understand it, I just kind of wrote arbitrary numbers for me to like understand it. But if you cut it at x, you can kind of think of it as distributed load concentrated at one point, right? So we can have that in the middle. So we have x, well in this case it's 4, but in general case it'll be x over 2, so at the point middle of the x. And then it would be the distributed load times the length, right? Because it's a distributed load concentrated at one point. So distributed load times the length. So that would be the force concentrated at this point at x over 2. So that would, same thing, force times length equals the moment. So length times force equals the moment, right? So now, and it's also negative because frowning face, right? It makes a beam frown, so that's not good. So we make that negative. I mean, it can be good, but I don't know. Yeah, what am I talking about? So the moment equals the principal of superposition. We just add them together, right? So the one that we got before, so the point load, and then the distributed load, and then we get the yeah, that's the moment with the input of x. So this is how the moment changes with x, and then we find the partial derivative of m with respect to f. So this is a constant since there's no f, so it's 0. And then here we find the partial derivative. So we take out f because the partial derivative of negative fx. We take out the f, and then x is a constant, or the coefficient, so x is remaining. So here we can plug it all the way back into the Castigliano's theorem that we got combined with the beam bending. So if you can kind of remember, this was in here, so we replaced negative x with the partial derivative of m with respect to f. And then we also replaced the moment. There's an m here, but we replaced it with this. So now we have here, and then let's see. And then yeah, from here we can take out the EI, the Young's modulus, and the moment of inertia. Make sure the computer doesn't shut down. Yeah, so you can take that, this is a constant, and then we're left with this. We can just distribute it, right? So negative x with negative, positive, negative x, negative, positive. And then x becomes squared, and then cubed dx. And then from here we can find the integral, so integrate x squared equals this, and then integrate that equals this. And then we plug in the L, so we plug in L here. So plug in L, and then we get this. And then can't forget the EI, so we put it here. And then, so if we remember the force I believe was 150, length was 60 inches. The check mark says what we know, right? So naming them off. And then the distributed load was like 5.833. L was 60. E was like 30 times 10 to the 6, and then I is 3.70. And then we just put it on a calculator, and then it gives us 0.1824 inches downward. Thank you so much for watching.